Good morning, everyone. Yeah, very good morning. Shall we begin the session? Yes, today's topic is loop unrolling. That is how to unroll or how to, we can say, change the loop or how to repeat the loop that is a repetitive task or that is used for the repetitive task. So loop unrolling is a program transformation that reduces the number of iterations for a loop by increasing the number of elements computed on each iteration. For example, we use a function, or example of this function is bsum2, where each iteration computes two elements of the prefix sum, thereby using or involving the total number of iterations required, whatever the iteration number required. Yes, in the last class we have finished with the decision statements. What are the various decision statements that is available within the loop? Okay. So let's start with the session. So we are using or we are studying about the loop unrolling. There are two methods for improving the performance. That is improve performance. There are two methods. One is a loop unrolling. First, it reduces the number of the operations that do not contribute directly to the program, in which we can further transform the code to reduce the number of operations in the critical path. And in this section, we are going to examine what are the various simple loop unrolling without any transformation. That means we are not able to change the loops, but we have to unroll the loops. This figure that shows a two-way unrolling that shows what are the various elements that are available with this. This is the figure. This is the loop or unroll the loop by two. There is a void combine. So we are combining this one. Vic ptrv data t destination long int I long int length equals to vec length v int limit equals to length minus 1. So we are taking the limit as a length minus 1. Then data t pointer data. We are taking the pointers variable because we have to fix the variable within the data. So this is the pointer data. Then get varchar or the vec start v. Then data t account equals to ident. Then combine the two elements at a time. For I equals to 0, I is less than limit, I plus equals to 2. Then ACC equals to ACC OP data I plus 1. Then finish any remaining elements or the combination. For I equals to 1, I is less than length, I plus plus. ACC equals to account OP operation then data I. Now this is unrolling loop vector by k equals to 1. In the same way, we are taking the k equals to 3, k equals to 4, whatever the looping we are going to, or whatever the looping we are, or we can say that the question arises. In general, the vector length will not be a multiple of the 2. We want our code to work correctly for the different vector length. We account for this requirement in two ways. First, we make sure that the first loop does not overrun the array bounds. For a vector of the length n, we set the loop limit to be n minus 1, and we must ensure that the loop will only be executed when the loop index satisfies the I is less than n minus 1, and we are going to use with the minimum array. We are use minimum array in the sense minimum data that is available. Minimum array index that is I plus 1 that satisfy the I plus 1 is less than n minus 1 plus 1 equals to n. And we can generalize this idea to unroll a factor by the k. So k is equals to 2, k is greater than 2, whatever the factor that we are requiring. So when we measure the performance of the unrolled code for the unrolling this one, that is k equals to 0, k equals to 3, we get the following result. This is combined 4, combined 5, 493, 501. Now this is the CPE performance for the different degrees of the loop unrolling. These are the 4 or the 6 looping. This is the unrolling factor. This is k equals to 1, k equals to 2, 3, 4, 5, 6. And it does not help the floating point operation, but it is used with both the addition and the subtraction, that is down to 1.00. That is, take the value as the float values. And the improving CPE for the integer multiplication is surprising, and we see that for the unrolling factor k between 1 and 3, the CPE is 3.00 divided by k. That turns out that the compiler is making the optimization code that is based on the reassociation transformation that alters the value in the way that how it is used with the CPE, how it is used with the k factor or the unrolling factor k. Now, when we want to load an array element from the memory and want to multiply with the accumulated result, we use the registers x and n, 0 to read and write twice in execution of the loop. And we can replicate this template n by 2 to show the computation for a length of the length or vector of the length n, obtaining the data flow representation. And we're still using critical path of the n operations in this graph, thereby using as much as or half of the many operations or iterations. Now, this is a graphical representation of the inner loop. These are the various registers, that is RAX, RBP, RDX, SM0, then load, mul, add, CMP, jump. Now, this is restricting the value that is used with the combined 5 operation as in data flow graphs. This is XM0, RAX, RBP, RDX, then load, mul, add, CMP, JJ. This is getting the compiler to the unroll the loop, and this is the critical path representation of the vector of the length n. This is the critical path. There is the load, mul, add. Now these are the various iterations. This is the iteration 0, iteration 1, 2, and 3. This is not the iteration, we can say this is the array from 0 to 3, then n minus 1, n minus 2, and n minus 1. Now, next is how to enhance a parallelism or how to use a parallel methods, that is how to make the bounds imposed by the data or how to limit the imposed as latencies available within the data. So when we talk about the enhancing the parallelism, that means what are the various functional units we are using. That means that runs in a parallel. So however, the function unit performing addition, subtraction that are fully pipelined, meaning that they can start new operations every clock cycle, and our code cannot take advantage of this capability. Even with the loop unrolling, since we are accumulating the value, we are taking out the value as a single variable accumulator. We cannot compute a new value for the count until the preceding condition computation has been completed. So until no one is completed, even though the function unit can start a new operation every clock cycle, it only starts one every L cycle, where L is the latency of the combined operations. And we will now investigate the ways to break this sequential dependencies and get performance better than the latency bound. So whatever the latency bound, whatever the sequential dependency that can perform, that can got the value performance better than the latency bound. The next is multiple accumulators. So for a combining operation that is associative and the commutative, such as integers, addition, multiplication, we can improve the performance by splitting the set of the combining operations into two or more parts. Whatever the two part that is taken out, that results in the two ends. And for example, let Pn denotes the product of the elements a0, a1, en minus 1, and assuming that n is even, we can also write this Pn equals to Pen equals to Pon, where Pen is the product of the elements with the even indices, and the Pon is the product of the elements with the odd indices. Whatever the data that is available, so that is used with the indices that is available with the I equals to 0. Yes, I equals to 0, n minus 1 ai, n by 2 minus 1 a2i. And this figure shows that the code will be used with this method that uses two-way loop unrolling to combine more elements per iteration, two-way parallelism, accumulating the elements with the even index in the variable accumulator 0 and the elements with the odd index in the variable accumulator 1. As before, we include a second round or second loop to accumulate any remaining array elements for the case where the vector element length is not a multiple of the 2 that is taken out. So this is the two-way parallelism. This is the combine 4, combine 5, 493, 510, 515. That is accumulate in the temporary, unroll by the 2, unroll by 2, parallelism by 2. This is 2, 3, 2, 3, 2, 1.50. There's a latency bound. Yes, there's a throughput bound. This is again the two-way parallelism. Void combine 6, vec or vec ptrv, data t destination, log int I, taken out as a length variable, that is a vec length x. Now, next is taking out the variable as a limit, that is equals to length minus 1. This is a program that shows how to unroll the loop by the two-way parallelism. This is void combined vec ptrv, then data t destination, then length equals to vec length, limit equals to length minus 1, then data t pointer, then indent or the ident, then accumulator 0, accumulator 1, then combine 2. For I equals to 0, I is less than limit, I plus my equals to 2, then acc 0 equals to acc 0 op data I, then acc 1 equals to acc 1 op data I plus 1. Then finish any remaining elements. For I is less than length, I plus plus acc 0 equals to acc 0 op data I. Then destination equals to acc 0 op acc 1. This is the unrolling loop by 2, and this is using the two-way parallelism that is available. That is the use of the pipeline capacity of the function unit that is used to improve the increasing value of the k. And for the integer multiplication and for the data verification floating point operation, whatever we are using the floating point operation, we see a CPP or the CP value of L divided by k. Well, L is the latency of the operation and the k is a length, or we can say the increasing value that is incremented by, for example, if I'm taking about the k equals to 2, that is incremented again and again by the 2. Now this is the CPE performance for the K-way loop unrolling with the K-way parallelism. And all of the CPE that is improved this performance up to the limit up to the 1.0. This is for the double, then float plus. These are the legend that show multiple lines, multiple datas. Now this is the graphical representation of the inner loop or the inner loop code for the combined 6. That iteration has a multiple instructions that is translated into the load and the mul operation. This is the load, then multiply operation, then again this is the load, then multiply operation, then add CMP JG. Again, there are multiple registers that is used for the various operation as a data flow. And we can simply use this to simplify and extract the representation to show the data dependency between the successive iterations, and there's no dependency between the two mul operations. So to understand the performance of the combined 6, we start with the code and the performance sequence. Then we can derive a template showing the data dependency between the iterations to the process shown in this one. And these instructions are compiled or translated into the mul operation that read and write separate registers with no data dependency between them. The next part is replicating this template n by 2 times, that is modeling the execution of the function on a vector flow diagrams on a vector area. And we now have two critical paths, each containing n by 2 operations. Then data 0, data 1, load mul add. Then data 2, data 3, again these are the 4 loops or 4 arrays that is used. The array size is 3, and that's going from, array size is 4, that going from the 0 to the 3. Then data n minus 1, n minus 2 and n minus 1. So this is going on till n minus 2 and the n minus 1. And the CPU performance is 4.00 divided by 2, that is L by 2. And once we reach this point, multiple function units are also operating at the maximum capacity with this one. That indicates that PEN might overflow or the PON might underflow. Next is how to reassociate the transformations. This is the formula, that is ACC equals to ACC OP data I, that is operation data I, then operation I plus 1. While in the case of the combined 7, it is performed by the operation ACC OP data I plus 1. That is used with the reassociation transformation because the parentheses shift the order. That means if I'm using parentheses over here, that shifts the operation with the accumulator with the array elements. This is the combined 7 program. We are taking two variables. One is of the vec ptr, one is for the data t destination. So variable names are the v and the destination. Then long int I, long int length, vec length v, long int limit, data t, data, get vec start, get data t, acc ident or ident. So this combines the two elements at a time. For I equals to 0, I is less than limit, I plus equals to 2. Then ACC equals to ACC OP data I plus 1. Then finish any remaining element. This is for I is less than length I plus ACC equals to ACC OP data I. This is for the unrolling factor K that gives the value as a, or take the value K equals to 3. And this shows a template n by 2 times to show the computation performed in multiplying the n vector elements. Now this is the data flow representation of the combined 7 with the length n. This is the critical path, data 0, 1, 2, 3, load, load, mull, add, load, load, mull, add. Again, this is load, mull, add. That is used to optimize the data element. So in summary, when we say about the reassociation transformation, that can also reduce the number of operations along the critical path in the computation. So if there are multiple operations, we can reduce the number of the path in the reassociation transformation. That reduces the number of operations also. That results in the better performance by the better utilizing the pipelining capability of the functional units. And most of the compiler will not attempt any reassociations of the floating point operations, since these operations are not guaranteed to be associative. And the current versions of the GCC do perform reassociation of the integer operations, but not always with the good effects. But in general, we have found that unrolling a loop and accumulating the multiple values in the piler is one of the reliable methods to achieve the program performance. Yes, this is one of the reliable method or the trustworthy method to improve the program performance. This is the product of an array of the n integers. This is a double A product, array product, A, N, I, X, Y, Z, 3 variables, and R equals to 1. I equals to 0, I is less than n minus 2, I plus equals to 3. Then AI plus 1, AI plus 2, R equals to R into X into Y into Z, that is a product computation. Then I is less than n, I plus R multiplied by equals to AI. Then return R. So for a line labeled product computation, we can use the parenthesis to create the 5 different association of the computation, that is as follows. Now this is a summary of the result of the optimizing combining code. That efforts are used as optimizing whatever the optimized performance that multiplies the elements of an array. So this is used for optimizing the combination that is used with the scalar code, scalar product, not making use of the SIMD parallelism provided by the SSE vector instructions. So this is SIMD code, SIMD plus 8-way unrolling 0.25 for the 6 gigaflags. Now some limiting factors are used in data flow representation also, that is used with the register spilling, with the computations in the assembly code, with IA32 instruction to set having a small limiting factors, number of register to hold the value that is being accumulated, and the degree of the parallelism P that exceeds the number of the available registers, then the compiler will resort to spilling, storing some of the temporary values on a stack. And once this happens, the performance on the can drop significantly. So this is the degree of the unrolling, IA32, 1, 2, 3, 4, 5, 6, then 2.12, 1.76, 1.45, 39, 90, 99. That achieved with now K equals to 4.